Alright guys, today we are going to be looking at quadratic functions. Okay, so we'll look at what they are, how they can be represented, and looking at some solutions for them. Okay, so we'll start off with what they are. So I've got a little hypothetical situation for you. Let's say you're standing over here and you have a nice good footy in your hand. Alright, and you decide you want to kick that footy. Alright, when you kick it, the ball's path is going to look something like this. Okay, the ball's going to go up, reach a peak, come back down, and who knows, it might actually be through the goal. So you might have hit the goal. Anyway, the ball's path, okay, so going up and coming down, and when it comes down it'll actually come and hit the ground, okay, this shape is called a quadratic, okay. It can be applied to lots of things with movement, okay, or motion. Almost any ball that you kick or hit or whatever, if you throw one off of the ledge of a building, alright, will have a quadratic shape about it, even if it's only some of it. So for example, with the throwing off the building, you might only have that second half there instead of this first half, right? It's just got the downwards path rather than, you know, the going up. What's another example? Okay, let's say you have a population, I don't know, let's say a beehive, alright? And you're plotting the population of these bees over time. So let's put T for time, and we'll put P for population of bees. All right. So we start off. Let's say there's this many bees. We don't know how much it is. Let's say, I don't know, 500. I can't say I know how many bees are normally in a hive, but we'll go 500. Let's say your beehive, a disease comes out. Okay. What's going to happen is your bees are going to start dying. So over time, your population will come down. Alright, and then let's say after a while, after you've been losing some of your bees, alright, they the ones that are immune are still alive and they've been breeding and they breed more bees. I'm not going to say I'm a bee expert, but let's say that happens. And what actually happens is the population makes a recovery. Alright, so the populations come down, and then the ones that are immune are still left. They start breeding, it comes back up, and it might, shoot up even higher. Okay? So again, this general shape, alright, if it looks like this, or this, alright, you have a quadratic. Sometimes we'll use all of the quadratic, so these arrows mean that these lines then go on forever, or forever up that way, alright? Sometimes we might only use part of it. So for example, in this example here, alright, it's sort of chopped off here, so you'll sort of chop our quadratic shape off there. And with this one over here, let's draw a pen around, the ball can only go from the ground up here, or ground down here, sorry, to the ground over there. So if the ground is here, you even put a line through, alright, our quadratic is actually this shape, but not the forever downwards. It would be if there was a hole in the ground and the ball could keep going, but that's not the case, okay? So that is the general shape of a quadratic. Okay, so it's important to remember, so I'll just do an example graph of an equation. Alright, so this is our x-axis, this is our y-axis. Okay, so for example, this particular one might look something like this. Alright, and it goes up forever that way, it goes up forever that way, okay? It's always important to remember that they're actually symmetrical, which means it has a vertex at the bottom here, the very lowest point, or if it was upside down, it would be the very highest point, where it has what's called an axis of symmetry, which basically means that it's mirrored from one side to the other. Okay. We did some work on linear equations earlier, so instead of having this sort of shape, it would just be a straight line. Okay, and we talked about those linear equations having a certain amount of solutions. Okay, so that certain amount is obviously infinity. Okay, so if a straight line goes on forever, alright, there's infinite possible, points on that line basically. Same thing with quadratics. We have solutions to our quadratics, and that's every single point on the line. So for example, here is a solution to this equation. It might be, let's just make up one, if that was 1 and this was also 1, alright, 1 and 1, or x equals 1 and y equals 1 is a solution of this equation. And we might follow it down, and down here we've got Well, that lines up with about 0.8 and about 0.5 there. So x equals 0.8 and y equals 0.5 might be another solution. And we've got all these solutions here, all the way around there, infinitely up that way and infinitely up that way. Okay, so it is important to remember that the shape of our graph is simply just the combination of all of our possible solutions. Okay, let's have a look at some examples about what the equation might look like. So you might remember that our linear equations were, as an example, it was y equals, say, 2x plus 4. Alright, that comes in the form y equals ax plus b. So that was for linear equations. Quadratic equations, a little bit different. Okay, the trick is it's got anything squared in it. It makes it a quadratic. There are some traps though, but let's look at some examples. So y equals 2x squared plus 4x minus 5. Okay, this is an equation. The reason being is because one of our variables has a squared term, alright? So that is squared. That makes this quadratic. It's as simple as that. It doesn't matter about any of this, okay? As long as that is squared, it's a quadratic. There is a little trap we'll get to later, but so far so good. Another example. Doesn't always have to be x and y, guys. A common one. So if we were talking about that football from earlier, we might actually say height and represent it with a h is equal to something like, we'll use t, it could be time, so time after the ball's been kicked. 5t minus 4, we're plus 6t squared. So again, alright, we've got this variable here is squared, which gives us a quadratic. Okay, so both of these are quadratic, as opposed to something like y equals 3x plus 1. Okay, that's not a quadratic because our x isn't squared, or there's no x that is squared. Okay, another example we need to be careful of. Let's put this one in red or pink because it's scary. Y is equal to, I don't know, let's go minus 2x cubed plus 4. So this one isn't a quadratic. The power up here is a 3, so it's x cubed, so it's not a quadratic. The highest power needs to be a 2. So over here, squared, squared, there are highest powers. Here it's cubed, so that's too high. Here there isn't a squared, so that's no good. Sometimes it can be hidden. So, for example, if we had something like y equals, let's go x plus 1, x plus 3, okay? On face value, we don't actually have a x squared here, do we? Okay, so we might be inclined to think, well, this isn't a quadratic. But in actual fact, if we expand these brackets, as I'm sure you'll remember from earlier this year, we can actually say that this same one, using FOIL, if we go firsts, well, x times x, well, that's x squared. Hello, that's our x squared term. I'll just quickly run through the rest. So it's plus 3x, plus x, and plus 4. So that'll be plus 4x, plus 4, okay, after doing the full expansion. So anything like this will always have some sort of x squared term at the front. So that's actually quadratic as well. Okay, so you need to make sure everything's as expanded as it possibly could be. Another example of that, let's go p equals q times q plus 3. Okay, again, when we do the expanding, we take what's out the front and multiply it by both things on the inside of the brackets. So we'll have p equals, well, q times q is q squared. Q times 3 is 3q. So again, we have a quadratic because we have a q squared there. Alright. We can also get deceived quite easily. For example, y equals, let's go x multiplied by x squared plus 2. Now we might be inclined to think, oh yeah, look, that's got an x squared. Alright, look, it's squared. That means we have a quadratic. When in actual fact, if we expand this out, okay, same thing as what we did down here. We just take what's out the front, multiply it by both things on the inside. X times x is actually x cubed. X times 2 is 2x. Okay, we don't actually have a quadratic because we have x cubed here, so that is not a quadratic. Okay, so I'm going to erase all this off, and we're going to look at finding a y value for any given x value. So what that actually means is that it means we're identifying one of our solutions. Okay, so if we get given any x value along here, okay, we can actually work out what our quadratic function is at that value. For example, let's say we want to know this point here is x equals 3, and we want to know what the quadratic function is there, which means we go down, we go, oh yeah, look, it's there, okay? And it's, you know, that might be y equals 1 or whatever it turns out to be. We can also look over here and go, oh yeah, x equals minus 1 over here, alright? The value of our quadratic, we can find there, okay? So that's basically what we're going to be doing, but we're going to look at doing it algebraically, because if we always use graphs, we're going to be using sort of, we're going to be looking at it, and it's going to be sort of a visual thing, and we're going to have to estimate what number it is, and we're not going to get an exact answer some of the time. So let's look at one example. So y equals x squared plus 4x minus 3. Okay, so and we want to know what this is at, we'll go x equals 2. Alright, first of all, let's recall what we did earlier in the year when we did evaluating by substitution. Okay, so we did things like 2a plus b, and we said, well, a equals, we'll just make this up, 3, and b equals, we'll go negative 2. Alright, the solution to that is you rewrite the line you just had, okay, but you substitute in what you're given into the expression we have, okay? So for example, everywhere we see an a, we're just going to put a 3, and everywhere we see b, we're just going to put minus 2. So we've got 2, well, a, we know that's 3, so we put 3 in, plus b, well, that's minus 2. Okay, work that one out. So 2 times 3 is 6, minus 2 is 4. Won't spend too long on that. Okay, so that was the general premise of what we did there, and it's very similar with what we do here. So I'm just going to erase that. That's getting in our way. Alright, so it's going to be the same sort of thing. So all I'm going to do is use my equation. I'm working out when x equals 2, so I'm just going to rewrite my equation, and everywhere I see an x, I'm actually just going to put a 2. Alright, so we've got y, well that stays the same, equals x squared. Okay, but instead of x, let's put 2. 2 squared plus 4x. Okay, so that's another 2. And minus 3. There's no x's there, so I can just leave that how it is. Right, and after that, all I need to do is just do the basic number work after that. So y equals, well, 2 squared, well, that's 4. 4 times 2, well, that's 8. Minus 3, well, that's still minus 3. 4 plus 8 is 12. Minus 3 is 9. Okay, so that tells me that on my quadratic, which of course is going to look different to this one, okay, at x equals 2, y is actually equal to 9. So on the one that I drew, it's going to be somewhere up here. So my quadratic might look like, I don't know, that. Okay, so that blue one. And so that's what we worked out here. So we worked out one of those solutions. We worked out the solution when x equals 2. Alright, let's just do one more quick example of that just so you get the idea. And again, it's not always necessarily x's and y's, okay? That's sort of like the basic or general form that we use. But we can apply it to whatever situation we're using. So the one we had before was the ball. We used height and time. And time is quite a common one. Okay, so you might use T for time and H for height. But let's make something up. Let's go m equals 5k plus 2 minus 3k squared. And we want to know what that is at, we'll go at k equals, we'll put 5 in. Okay? So, what we do is we just simply substitute this back into the equation. Everywhere we see a k, we're going to put a 5. So we've got 5, whoop, there's a k straight away. So in it comes in there. Then we've got plus 2, well that's alright. And we've got minus 3k k squared. And instead of k... Oh, hang on, I made a mistake. Sorry, guys. What was I meant to do there? Let's put a 5 in there, of course. Otherwise, I wasn't changing anything. So we'll put a 5 in there and a 5 in there, because the k there becomes a 5 and the k there becomes a 5. Everything else is the same. Again, it's just number work from here. So, well, 5 times 5, that's 25, plus 2. So, we'll do this slowly. So, 5 squared is 25, but then it's multiplied by minus 3. So, that's actually minus 75. Okay? M equals 25 plus 2 minus 75. I think that's about minus 48. Okay? And we have found the solution. So you actually sit here and say, solution, you go k equals 5, m equals minus 48. Okay, we didn't do that for the last one, alright, but we still found it. Okay, so that's the general idea. So you guys will now get a set of questions to do with doing these sorts of problems and identifying quadratics as well. Okay, and then you'll complete those before you move on to the next video. Okay, so thanks for watching, and I will see you in class.